Chapter 11, Part 1, Rotational Dynamics and Static Equilibrium. So let's just start with this thought question first. So you have a flat tire and need to remove the lug nuts to change it. Where do you push on a wrench to turn the nuts and why? So I want you to think about this for a second. If you're changing this tire, where do you push on this wrench? Do you push right here? Or do you push right here? Okay, so think about this. So another question. You come across a very heavy door. A sign on the door says to push or to open. Where should you push? A, near the hinge. B, in the middle. C, as far away from the hinge as possible. So the answer is C. We'll get to that. We understand why, but we don't really know what the physics is behind this. Okay, so we're going to understand this by the end of the chapter. So let's talk about torque. It causes an angular acceleration. Okay, so we remember what the angular acceleration was. It was alpha, right? And it is analogous to a force causing a linear acceleration. We remember what the linear acceleration was. It was A, right? The force causing a linear acceleration, F, was ma. F equals ma. It was this Newton's second law of motion. So here's the definition of the torque. It is a force times the length that is perpendicular to the axis of rotation. Or if you want to see a general rotation, which is, I prefer this general rotation because it will be always 100% correct. Torque is R cross F. So they are both vectors, both F, which is the force being applied to an object, and R, which is the radius, which or the radius, or the distance from the force to the axis of rotation. If you make a cross product out of these two vectors, you will get a quantity called torque, and it is also a cross product at the same time. So this is the magnitude of R times the magnitude of F times the sine of the angle between them, sine of phi here, for example, or sine of theta. Okay, so if you remember, we had two vectors, for example, vector A and vector B. Okay, and if you make a cross product out of these two vectors, A cross B, and let's say that this is theta, then a cross product of these two vectors will always be perpendicular to both vectors. Okay, kind of like that. So it is perpendicular to B, it is perpendicular to A, and it is A, B, sine of the angle between them. So let's take a look at this merry-go-round. Only the tangential component of the force causes the torque. Okay, so in other words, if I have a force being applied to this merry-go-round like that along the radius, this will be a zero torque because this wouldn't change anything. But if you're applying a force to this direction, okay, so if you're applying a force with an angle, only a part of the force that is completely perpendicular, okay, to the radius, or tangent to this radius will do the work. In our case, this is F sine theta. So if you're applying a force of F, and this is the theta over here, this F will have a linear, or towards the radius component, and another component that is tangent. So you need to find each. In other words, you need to break down the force into its components. So F is F cosine theta in this direction and F sine theta in this direction. Okay, and this one doesn't do anything. because this is literally the same thing as this guy. But F sine theta is doing work for us, or in other words, it's causing the torque, or it's causing the angular acceleration. So this will cause alpha, or angular acceleration in our case. So torque and direction. The torque is positive when the force tends to produce a counterclockwise rotation about the axis. And we also know that we consider omega being positive if it's counterclockwise, and omega, which is angular velocity, is negative if it's clockwise. In other words, if you remember, this was a positive omega, okay, and this was a negative omega. And these omegas were, this is counterclockwise, and this is clockwise rotation. Okay, so it's the same thing for torque. If you care for this direction, so it produces a counterclockwise rotation, and then that we call it a positive torque. Okay, the unit for torque is so let me just write down the formula for it. Okay, so that's RF sine of the angle between them. And if you're looking at this, sine is just a value, it doesn't have any units. It is R, which is in meters, and F, which is in newtons. Okay, so we know what the F, we know what the Newton times meter is. It's joules. Okay, so it's in the units of energy. So what you can see here is torque is actually causing the change of the energy of this rotating object. Okay. All right. Which is, by the way, equals to kilogram times meters per second square. Or in other words, kilogram times meters square over a second square. So torque as a vector. Torque can be expressed as a vector. It is a vector. I just showed you that it is a vector product. Using the vector product, right-hand rule, and this is the book suggestion of the right-hand rule. I will show you another way. So place your thumb in the direction of the first vector in the cross product. In this case, it is R. So, so if I have R here, okay, it's a vector, so it has both a value associated with it and a direction associated with it. Okay, and then place your fingers in the direction of the second vector in the cross product, which is in this case F. Let's say that this is F. Okay, that's the angle between these two. Then right-hand rule says your palm gives the direction of the result of the vector multiplication. So in this case, which is tau. So in our perspective, this would be tau, and it's a vector. And this is 90-degree angle. This angle is also 90 degrees. Okay, it's like a corner of your room. The way that I look at it is that you can put your four fingers along the direction of the R. Okay, so point your four fingers across this direction. Okay, and you want to bend it towards F. Okay, so wherever the F is, if it's right there, you want to bend it in this direction. Okay, and then your thumb will show the direction of F. Okay, so put your four fingers along the direction of R, bend it towards F, and then your thumb will show the direction of tau, which is torque in this case. So Newton's second law for rotation, remember Newton's second law is not only for linear type of motion, but it's also for rotating objects. So in a linear type of motion, we had F equals ma, that you can see here. In our case, we put a subscript of t, which means tangential. or tangent to the path, or tangent to the rotation. But we know that torque is F R, okay, or F of tangent over R, all right? And A here is A of tangent, and we know what the A of tangent has a relationship with a, rotational acceleration alpha through this relation here. I have proved all of these in the previous chapter video, okay? Chapter 10. So go ahead and watch that if you don't remember it. But remember that A of tangent is R alpha. I have solved a couple of examples when it was asking for tangential acceleration. So if you substitute these two into the formula that we have on top, F equals ma for the tangent force, then what you can find here is that tau is mr squared alpha, okay? All right, so now this mr squared is moment of inertia. We remember that. We remember it from the kinetic energy in the last chapter, in chapter 10. Remember the kinetic energy, rotational kinetic energy? I solved so many problems using this in the previous video. So Kf sub r is half I omega squared. Omega was a rotational velocity, okay? So this I was moment of inertia right there. And for an object, for example, a ball of mass m rotating around the axis of rotation, right there, and with a distance of r from it, so this is r, then the moment of inertia would be mr squared, okay? So in our case, tau equals mr squared alpha, and this mr squared is just the moment of inertia. So if I have a torque of not only one object, okay, but a object that is composed of many other objects, okay, a system of objects, for example, M1, M2, M3, M4, and so on and so forth, okay? So in other words, if there is no, if we consider that these objects are not interacting with one another, okay, and the only force that is being applied to these objects or to the system of objects is only external force, then I can write the total or external torque acting on this system is equals to the sum of all the moment of inertias times alpha, which is the rotational acceleration. In other words, I have to sum the total torque is torque on object 1 plus torque on object 2 plus torque on object 3, and so on and so forth. So I have to add all of these up, tau 1, tau 2, tau 3, and all the way to the last number of tau n. Okay, each of these objects have a m, or a mass, and then they have a specific or particular r, or radius, from the axis of rotation. For example, m1, r1, m2, r2. Okay, so I need to know the exact value for each object in the system and then try to add them up. The problem in this case is if we have a solid object, let's say a sphere or a disk, then it's composed of millions of these little objects, these points, okay? So it's impossible to add a million of these torques for each object together to find the final number. So what we do is that we introduce the total torque, or the net torque, of sum of all the moment of inertias, okay? So the moment of inertia times alpha, the moment of inertia of an object. You know what this is for a sphere, for example, for a solid sphere, for a hollow sphere, for a cylinder, okay, for a disk, For a donut, you know what I is. It's usually been given by the problem. Okay, this is usually given. We know what the value for this is. And alpha is the rotational acceleration, which for all of these objects should be the same because they're all moving with the same rate. It's also very important to note that when we're talking about this, all of the internal forces will cancel out. These are action-reaction pairs, and we do not consider them as a force that will cause the torque, okay? These are action-reactions. For example, F of 3 to 4 is in this direction, and from 4 to 3 is in this direction. So both of these objects are in this away from the axis of rotation from the same distance. So this R and this R would be the same. You have two forces. One is to this direction, the other one is to the opposite direction. So they will cancel out. So all of the internal forces will cause no torque or no change in the torque. So what we do is we consider the external force or external torque in this case. Remember, when I say force and when I say torque, I am talking about the same concept. Force is causing a linear motion. Okay, so F is causing linear A, or motion or acceleration, but torque is causing rotation. Okay, rotation or rotational acceleration. So we have to remember that. But they have the same concept. They have the same, concept behind them in physics. Rotational analog of the second law. So net external torque equals moment of inertia times the angular acceleration. This is the exact analogy that we use for linear second law. The linear second law was telling me that sigma F or F of net or F of external is MA. This is the exact same analogy. I have sigma tau, okay, or tau of net, or tau of external, okay, is I alpha. A is a linear acceleration, alpha is rotational acceleration. M is just the mass of the object. I is moment of inertia, which not only depends on mass, but also depends on the configuration of these masses, because R, or the radius, is also important. Okay, so the requirement here is also that angular acceleration must be expressed in radius per second square. Radians per second square. Let me go ahead and highlight it because it's extremely important. Okay, so as I said, we have the same analogy. We have whatever that we have in a linear motion, we'll have the same concept in the angular motion. So in linear motion, we have M. In the angular motion, we have I, okay, which is the moment of inertia, or depends on the mass, mr squared, okay, or it depends on the shape, okay, so it depends on all of these objects, all of these little particles that makes the object. In a linear type of motion, we have acceleration A. In the angular type of motion, we have alpha, angular acceleration. For the linear quantity, we have F, or force. For the angular quantity, we have torque, or tau. Okay, so they're all having the same concept. One is for angular motion, the other is for linear motion. So, problem-solving strategy. First is if the target variable is force, torque, or acceleration, try using Newton's second law, okay, for rotational instead of energy. So start with the second law first. Sketch the situation, identify bodies to be analyzed, indicate rotation axis. 3, draw a free body diagram. It's always a good practice to do that, always. That shows its shape include dimensions and angles needed for the torque calculations. 4, choose an axis. If you know alpha, choose that direction as positive. So the direction of motion, or the direction of alpha, to be positive. Decide if each body undergoes translational motion, rotational motion, or both. Okay, so it depends on the problem. Express geometrical relationship, angular quantities in terms of linear quantities. And the last one is make sure you have as many equations as you do unknowns. So if you have 3 unknowns, you need 3 equations at the minimum. So let's take a look at the equilibrium. Conditions for equilibrium. First condition is the sum of all forces is equal to 0. So if you add all the forces, they have to end up to be 0, both in x direction and y direction. Okay, if in x direction they will end up being 0, but in y direction they don't, so you don't have the first condition. Second condition, and they have to be satisfied at the same time. Second condition is that sum of all torques about any given point, this is very important, any given point is equal to 0, or sigma tau equals to 0. These two are the two very important, and they have to be true at the same time. So first condition, the sum of all the forces equal to 0. Second condition, the sum of all the torques equal to 0. Let's take a look at 3 cases here, okay? So let's take a look at case number A. This body will stay in a static equilibrium because it will both of the conditions will be satisfied. So the first condition is you have 2 forces up, okay, both on the side, and then you have a force of a double magnitude, a 2F down from the center. So no net force is acting on it. We have 2Fs up and the 2F down. They will cancel out, okay? At the same time, this 2F is not applying any torque because it is, the R is 0 for this force 2F. Okay, so for this 2F, R is 0 for 2F. But for these one of them will tend to make this disk rotate this way. The other one is causing the object to rotate this way. One is clockwise, the other is counterclockwise, so they will cancel out. So you have both conditions satisfied. So this is staying in the equilibrium. Let's take a look at B. This body has no tendency to accelerate as a whole, but it has a tendency to start rotating because you have an F up and you have an F down, okay? So they will cancel out along the y direction. There is no F along y, and there is no F along x. But this F will cause the rotation in a clockwise motion, and this F will do the same. So this object will start rotating, so the second condition is not satisfied. There is a net torque in this object. And if you're looking at C, so C is asking, the first condition is obviously not satisfied. We have a total force of 3 Fs up, okay, as you can see right here. So we have 3 Fs up, 2F and 1F will give us 3 Fs, okay? So the net force along y direction is not 0. So the first condition is not satisfied, but the second condition is satisfied. If you're looking at this, you have an F acting in the distance L around this point, which is the axis of rotation, causing the object to rotate clockwise, okay? So you have F times L for torque. And then you have another torque. So let's call this torque 1 and torque 2. Then you have another torque, 2F, acting on the distance of L over 2. Okay, but this will cause the motion to be counterclockwise. So you can consider one to be negative, the other one being positive. They are in the opposite direction. Let's call this one negative. So you have negative FL, and then you have positive FL. So the total torque, which is torque 1 plus torque 2, is 0. So the second condition is satisfied. But this one is still not in equilibrium because the first condition is not. So in other words, you have to have both conditions satisfied at the same time. Another very important point to find equilibrium is that if the net torque is 0, okay, so in other words, if your total torque is 0, then it doesn't matter which axis we consider rotation to be around. So you can choose this axis, for example, in this example, to be an axis of rotation, okay? Or you can choose this to be the axis of rotation. So we are free to choose the one that makes our calculations easier. For example, if we choose this axis of rotation, we have F1 acting on this system or acting on this object from 0 distance from the axis of rotation. You have mg from axis 3/4 of L from the axis of rotation. And then you have F2 acting upward in a distance of L from the axis of rotation. Okay? If you consider this to be the axis of rotation, then you have mg acting 1/4 L from the axis of rotation, and then you have F1 upward in a distance L, acting in a distance L from the axis of rotation. It does not matter which axis of rotation we consider to be our rotation point or axis of rotation. So we generally use the one that makes our calculations a bit easier. Okay, this is the end of part 1. In part 2, I'll go over some examples. So if you have any questions, let me know. Otherwise, go directly to part 2 and watch the rest of the chapter.